Water conservation. Obviously, this is a big topic, not only here in Seattle. I mean, the California has got a 2020 event going on. We're trying to reduce 20% of their water by the year 2020. Florida's got a big water conservation effort going on there. And since the buildings and hospitals and universities are the biggest water consumption, normally they're cooling towers next to landscaping. It certainly takes a good look at where we can go with water conservation. And one of the topics I'm going to spend a couple slides on is what we call concentration ratio, or cycles of concentration. The more you can concentrate that water, because steam is leaving the tower at the top, so all the minerals stay behind, the more you can cycle that up, the less water you're going to use. And it's pretty drastic. Going from, think about water in, water out is probably the worst. I mean, it's water in, water out, okay? If you go down to 2 cycles, you drop almost 50%, well, you drop 50% water usage, okay? From there, for 3 cycles, you drop a fairly good amount, incremental amount. 4 cycles, 5, 6, 7, 8, 9. There is a diminishing return. Okay, you can see the graph coming down, and eventually it's going to go way out here. It'll never reach 0. 0 obviously is 0 discharge. You just don't discharge anything. Okay, so you can see the incremental savings here is not as great, but still worth capturing. But if you're running up in here, then the savings are very drastic. Okay, so the definition of concentration ratio is basically the ion concentration in the recirculating water divided by the ion concentration of the makeup water. Okay, that determines your cycles. For example, the conductivity of city water here is about 74 micromoles. Okay, if your tower runs 740 micromoles, so you're concentrating it up, you're running basically 10 cycles. Okay, 740 divided by 74 is 10 cycles. At 10 cycles, you're running about 10% bleed rate. So in other words, all the water going to the cooling tower, about 10% is being removed through bleed. Okay? The higher you go, the smaller percentage of your bleed rate. Obviously, the lower you go, the higher percentage of your bleed rate. So what does that mean? Well, when you look at the water's ability to either be scale-forming or corrosive, there's a couple models in the industry. So I'm going to use LSI for the purpose. This is basically a Langler Stability Index. It basically takes things like calcium, alkalinity, conductivity, pH, puts it in a model, and predicts whether the water is going to be scale-forming or corrosive. Okay? We can change that model. We can change it. If we cycle up the cooling towers, we actually have different numbers. So as we go up in the LSI scale, we seem to get more scale-forming. As we go down the LSI scale, we get more corrosive. Most water treatment programs can handle an LSI of 2.5. Once you exceed 2.5, the chemistry itself really can't handle all the calcium alkaline in the water. You can still scale on top of it. Okay. So what we use this model, so what I did is I plugged in Seattle water into this model and did some calculations on it to find out where you should be. Based on the LSI, the cooling towers can operate at 15 cycles of concentration in Seattle. Okay, 15 cycles. You're way out here on that graph. Okay, which is very good. Now you need good water treatment program to prevent scaling, because as you push it out there, you are going to see some deposition if you don't have good water treatment. So your conductivity set points on all your controllers should be around 1,000 to 1,100, unless you have varying makeup source waters. So one of your homework assignments is when you go back to your cooling tower controller, see if it's between 1,000 and 1,100. If it's not, ask your water treatment supplier why it's not there.